Hello, my name is Keith Packard. I work in the Device OS group at Amazon as a senior principal engineer. Today I'm going to talk about Picolibc, a C library designed for embedded 32 and 64-bit microcontrollers. In this presentation, I'll describe what I see as the requirements for an embedded C library, the pieces from which Picolibc was built, how development progressed, results of that development along with several projects that have Picolibc support integrated into them. Finally, I'll briefly touch on future work that I hope to see done in Picolibc. Embedded systems generally make modest demands on the C library. The most commonly used functions are string and memory APIs, things like strcpy, memmove, and the like. Applications doing computation may need some math functions like square root sign or the occasional Bessel function. Standard I/O will often only be used during debugging to send output to a serial console to help diagnose software and hardware issues. However, applications may also use these functions to handle JSON, YAML, or other text interchange formats, and so strict standards conformance can be critical. While I am a strong proponent of share-alike licenses, a C library needs a pragmatic approach to be useful to all developers. A clear MIT or BSD license is best practice in this space. When I started doing embedded development in the modern era in 2009, I was using an 8051 SoC. The compiler, SDCC, came with a small C library, so I didn't have to think about it. In 2012, when we built our first Cortex M3 board, I also had to find a new C library. For this project, newlib was too big and required too many support routines in the form of libgloss, including sbreak from alloc, which was required for standard I/O. I initially settled on pdclib, as that was at least reasonably small. However, it used a lot of stack space for printf and didn't have a math library. This library seems to be an experiment in building a small C library, but not in building a C library for small systems. Some SoC vendors provide proprietary C libraries. These are often ports from older 8 and 16-bit systems which can lack compliance with modern C standards in some areas. And of course, they're not free software, which makes them uninteresting to me. After a couple of years of using pdclib, I decided to return to newlib and see what can be done to make it usable for my work. I want to say first that newlib is a great project. The code is easy to work on, the community is welcoming and supportive, and I've been happy to collaborate with them. Everything here relates to using newlib for my small embedded projects, which is not what newlib is really designed for. In looking at the changes that I wanted to make, the first thing on my list was standard I/O. Newlib's standard I/O is designed to offer good performance and full compatibility on systems with an underlying POSIX API. It has internal buffering and allocates space on the heap for them. Replacing the whole thing seemed like the best option. I also wanted to get rid of the libgloss OS shim layer. Libgloss was originally designed as an interface between newlib and whatever underlying operating system it was run on. With bare metal environments, there is no operating system, and so there really isn't a reason to have this library anymore. Newlib uses POSIX interfaces internally. Porting to an RTOS is usually a simple matter of making sure the necessary POSIX interfaces are available. Fortunately, most of the common uses for libgloss APIs were in standard I/O. By replacing that, the bulk of the problem was already solved. One other huge consumer of RAM in newlib is the struct reent. This structure holds all per-thread state for the entire library. Replacing this with modern thread local storage techniques would free up a lot of memory while still allowing applications to take advantage of library APIs which needed persistent state. Newlib is an old code base that has seen development extended back to the pre-ANSI era of compilers. The C language has changed a lot since then, and how we use the language has changed even more. It's been a long time since I defined a new API with a bare int type. We now know that it's best to use a more specific type that won't surprise you with overflow issues or sign errors on some new platform. At a minimum, the library should compile cleanly with WAL, WExtra flags. Finally, it's unreasonable to expect code review alone to catch errors and changes to the library. An extensive and automated test suite is table stakes for a project of this size. I got started hacking on the standard I/O changes that I wanted to make and sent them into the newlib mailing list to see what feedback I might get. That was when the reality of what newlib was hit me. Newlib is not a library for embedded application. Newlib is the Cygwin C library, which happens to be used by many embedded developers lacking an alternative. In particular, radical changes to the API and ABI of the library could never be integrated, as those would break binary compatibility for Cygwin applications. So I decided I had to fork newlib and start a new project. Once I decided to abandon attempts to upstream my work, I felt free to make all the changes I wanted, building the libraries I thought best. The good parts of newlib I kept. The math, string, and locale implementations work great. Having had experience with AVR Libc on Atmel processors, I took that code as the basis for a new standard I/O implementation. To get rid of struct reint, I decided to replace it with thread local storage as supported by the C language. That involved changing nearly every file in the library, removing the parameter from internal functions, creating new thread local versions of all global data. The tests needed to run on target architectures. Picolibc includes enough infrastructure to build and run applications on bare metal hardware without depending on any external software. That includes startup code, linker scripts, and a mechanism to get error codes out of the test and up into the test framework running on Linux host. These are also what developers need when starting to work with a new chip. Changes to move the code base from the old style C to more modern practice were made so that Picolibc now builds with a C18 compiler and builds cleanly with GCC and Clang's wall, wextra flags. Newlib also uses an old style build system with a maze of autotool bits and nested configure scripts. Instead of modifying those, I decided to overlay a new build system on top using Meson. This had a couple of advantages. First, it meant that I could ignore the existing build system so that upstream changes to that wouldn't affect merging my code changes in. Second, Meson builds are dramatically faster. A full build for all embedded ARM targets, compiling 28,429 files, takes only 38 seconds with an empty compiler cache. With the cache hot, that same build takes but 6.3 seconds. For some internal testing, I reanimated the newlib test suite and then started adding more tests. Newlib includes piles of GPL code, but none of that is likely to be used in a non-SIGWIN binary. To make the Picolibc license status clear, all of the non-BSD licensed library code has been removed. The printf test cases came from a GPL license testing project, but those are not part of any possible library build. Now I'll start going into some of these changes in more detail, starting with the math code. One of the most useful bits of newlib is the math library. That includes implementations of the standard math functions as specified in IEEE 754, NCC, and POSIX. Lots of this code came from Sun back from the early 1990s. A couple of years ago, ARM provided some new float code using double precision intermediates to reduce the number of instructions necessary for these operations. Unfortunately, the resulting code is less accurate than the old Sun code. And of course, it's really only useful on hardware that has 64-bit floats. As a result, Picolibc disables this code in default builds. Some of the math library code is split into two layers, a lower-level IEEE 754 API, which does the computation, including raising exceptions on hardware that has them, and a higher-level C API, which uses those lower-level functions and also updates the error no as appropriate. The library can be built without error no support, which eliminates these C wrappers and exposes the IEEE functions using the C names. These functions should be squashed together, moving the error no bits into the lower-level functions. NCC has slowly refined the use of error no and now has relatively consistent behavior based on the underlying IEEE 754 exception definitions. POSIX constrains behavior further. For instance, C17 says that a domain error may occur for POW 0,0, but provides no hint to the value returned, while POSIX requires the return value to be 1 and also requires that no errors are raised. Picolibc code has been modified to follow the POSIX spec as closely as practical. Exception generation relies on executing instructions that raise the appropriate exception, and that is challenging when C compilers work hard to move computation from runtime to compile time. I don't know of a surefire way to force a particular computation to happen at runtime. We've adopted some techniques which work with existing compilers, but we'll need to keep testing the library to make sure compilers don't outsmart us in the future. With the Picolibc testing infrastructure in place, tests were added to verify error no and exception values for all math library functions and all exception causes. Picolibc inherits its standard I/O from AVR Libc. This code uses a small in-RAM struct to hold per file state. Picolibc's standard I/O is built on two primitive operations, get a character and put a character. Any file struct includes pointers to functions which do just that. This means that implementing I/O for another system involves implementing just these two functions, not a large set of POSIX APIs. To make Picolibc's standard I/O code reentrant without requiring locking, the unget field is manipulated with atomic operations. As this field gets modified at runtime, the struct itself needs to live in RAM. There are macros which help applications initialize the structure correctly, also inherited from AVR Libc. Standard in, standard out, and standard error are global pointers to file structs. They are declared const as Picolibc doesn't modify them, and so that they may be placed in ROM. These can all point to the same underlying file object if desired. For systems that do support POSIX functions, Picolibc provides fopen and friends using those. fdopen creates a file struct with getc and putc pointing at functions inside Picolibc, which then use POSIX read and write. This support doesn't extend to fseek or rewind currently. Those are not yet implemented, although they could be added fairly easily. The standard I/O code has made some obvious trade-offs for size and simplicity versus performance. Funneling all I/O through narrow 1-byte functions slows things down. There are also no multi-byte or wide character support. For my applications, those have seemed like good choices. I'd like to hear what other people think. Printf, and to a lesser degree scanf, are key functions for any C library. When used for debugging, they need to be small and avoid interfering with other parts of the system. When used for data interchange, they need to be NCC and POSIX compliant. The original AVR Libc printf is remarkably tight and has only a few issues with standards conformance. The one major gap is in printing and scanning floating point numbers. These are fundamentally base conversion functions, converting between the base 10 printed form and the base 2 internal form. Think about how 1/10 is represented in binary form as an infinite repeating fraction. This makes exact conversion impossible. So I'll redefine exact float string conversion as a conversion where a number printed and then rescanned generates exactly the same internal bits. Newlib, glibc, and other C libraries use arbitrary precision numbers for this style of exact conversion. This is slow, large, and generally requires malloc. Picolibc uses the RIOT fixed precision algorithms developed by Ulf Adams to perform these operations. These require 128-bit operations for double and 64-bit operations for float conversions. This reduces code size and avoids malloc calls. Picolibc has numerous additional fixes and improvements, including hex format floats, so that it nearly meets C18 requirements, the notable exception being numbered arguments. Newlib was developed before threading was common in POSIX environments. In that era, there was no C language support for thread local storage. To work around this, Newlib introduced struct_reint. This struct contains every variable in the library which needs to be thread-specific according to POSIX. That includes common things like errno, but also rarely used items like sign_gam, the global variable used to hold the sign return from L-gamma. This struct uses 656 bytes on ARM32-bit. Newlib Nano includes changes which dynamically allocate much of the struct as needed, reducing the static size to only 96 bytes. But Picolibc eliminates the struct entirely, instead using the C language thread storage class. The linker gathers all of the variables of this class, effectively creating a struct on the fly. Only TLS variables used by the application end up in the application. At runtime, access to these values uses an ABI-specific mechanism. For some architectures, Picolibc supplies helper functions for this. Picolibc also provides functions to allocate, initialize, and set up ABI-specific mechanisms so that applications can manage multiple TLS blocks without needing a detailed understanding of the target architecture. We'll see this later in some examples. Testing is key to the success of any system software like Picolibc. Because most of the library will not be used by any one application, it's difficult to do in situ evaluation of the code. Instead, explicit low-level tests are needed to ensure the library conforms to the expected definitions. Fortunately, C libraries have several comprehensive specifications that define library behavior. This makes building a test suite a matter of identifying statements in the specifications that can be converted to assertions, then writing code to test them. Newlib had an existing test suite which was not working when I found it. Fixing those tests and getting the code passing again took several months. The code fixes were shared with Newlib, but there was no way to fix the test suite in Newlib itself, as it doesn't have any way to run tests on the target systems. To validate the tests, they are all run against both Picolibc and glibc. Picolibc contains numerous architecture-specific code paths, optimizing for space and speed using a combination of special C code and handwritten assembly. The target architectures have varying characteristics as well, from floating point support to sizes of basic data types and even signedness of the char and wchar-t types. Making sure all this code operates correctly can only be done by executing on all the target architectures. Picolibc does this by building bare metal tests for each architecture and then running them under QEMU, which avoids needing a pile of sketchy embedded hardware for testing. Bare metal code requires hardware-specific support in the form of starter code and linker scripts. Finally, the tests also need some way to report status back to the test harness, which uses the semi-hosting support in QEMU. QEMU includes support for numerous ARM architectures, but not all of the supported CPU types are actually available. Any non-Cortex-M CPU can be used in the None machine, but there's no equivalent for Cortex-N CPUs, which are only available in full SoC models. As a result, only the Cortex-M3 CPU can be tested in upstream QEMU. I submitted a patch adding a virt-M machine that enabled testing of all Cortex-M models in QEMU, but that was rejected as out of scope for QEMU upstream. Within the upstream newlib source are thousands and thousands of tests. Essentially, none of these work, having been neglected for years. The math tests appear to have been translated a number of times, corrupting the expected values. Places which should have been nan or inf have been replaced with 64. Fortunately, the test code also contains paths to compute the expected values by calling the appropriate routines. I regenerated all the tables by using Libc as an oracle. New tests have been added to the test suite code as well in response to bug reports. With major rewrite of nano-malloc code, extensive malloc validation and stress testing was used to make sure it works in a wide range of environments. An external printf test suite was incorporated to make sure changes to printf continue to produce the expected results. Finally, a sequence of bug reports against newlib's math routines, which reproduced incorrect exception and error no results, led to the development of tests against all libm functions to make sure they produce the right error no and exception values. To make sure the tests continue to work correctly, they are built against glibc and the output verified for that library as well as Picolibc. With the tests reconstructed and a test harness built that uses QEMU to run them, all of the tests now pass on ARM, AR64, RISC-V, and x86 today. Here's a program that shows the size of Picolibc's printf function. Unlike the first example, this one includes an argument so that it isn't converted into a call to putS. We use a floating point number to show the size of the different versions of the printf provided in Picolibc. Using a bit of symbol definition magic, Picolibc lets you select which type of printf function your application will use at link time. Because of the way floating point numbers are passed to var-args functions like printf, we need to use printf float to handle the 32-bit float value. When using the float-only version of printf, this inline function wraps the 32-bit float in a 32-bit int, preventing it from being extended to a 64-bit double. When not using the float-only printf, this function casts to a 64-bit double. This example can be compiled and run like the Hello World example above. This table shows the different size of the variants. The first is the full version of printf supporting 32 and 64-bit floats. The second only provides support for 32-bit floats. The third has no float support and doesn't support 64-bit ints. To add 64-bit int support would increase the size by 400 bytes. I also included sizes for the original newlib code, both full float and integer only. These show the initial RAM size plus the amount of memory allocated from the heap at runtime. You can see from these numbers why many developers avoid printf in standard I/O, often writing custom I/O routines. Adapting the AVR standard I/O and printf code, along with the RIU floating point conversion code, provides a standard I/O that fits in most ROM budgets while using very little RAM. Now I want to talk about work done in other projects related to Picolibc, including toolchains, operating systems, and hardware emulation. The INRIA CompCert project is building a formally verified C compiler for embedded software. Projects using this compiler would prefer a C library also built with a verified compiler. CompCert developers have provided patches to Picolibc that allow it to be built with their compiler. Most of these changes fix GCC and Clang-specific language constructs in the code, and so they have generally improved the portability and C standard conformance of Picolibc. Crosstool-NG is a cross-compilation toolchain building system. Select a target system and a suite of libraries, and Crosstool-NG will download the bits, build the host tools, compilers, and libraries, creating a self-contained toolchain ready to build your embedded projects. Zephyr uses Crosstool-NG to build its native toolchain. One of the assumptions built into Crosstool-NG is that there's only one C library. For most users, that's pretty reasonable, as they only need to use one C library to build their projects. And that's how initially integrated Picolibc into Crosstool-NG, offering another C library alternative to newlib and newlib nano. With a resulting toolchain, I managed to build and test numerous applications, including the Zephyr tests. However, that's not how Zephyr project was using Crosstool-NG. Within the Zephyr fork of Crosstool-NG was a kludgy patch to build both newlib and newlib nano. This allowed Zephyr users to download a single tool chain and decide while building their Zephyr project which C library to use. I decided to work from there and create a mechanism that could be upstreamed into Crosstool-NG that would build all three C libraries, Picolibc, newlib, and newlib nano, and offer the users a mechanism to select between them while building an application with a toolchain. Working within the Crosstool-NG community, we ended up using the companion library mechanism for newlib nano and Picolibc to build these in addition to the core newlibc library. You can also ask to build only one of the three, although the configuration mechanism is a bit clunky. Taking advantage of the libstdc++ patches incorporated into GCC, Crosstool-NG also builds libstdc++ for all three libraries. All this work is now in Crosstool-NG. Many of you are probably familiar with Zephyr, the embedded operating system sponsored by the Linux Foundation. I got interested in when I discovered they were getting serious about memory protection stuff. An embedded operating system that took advantage of memory protection hardware available in smaller SoC devices sounds like a good thing to me. The Picolibc integration work started about 2 years ago. I sent an initial pull request that included TLS support for 32-bit ARM processors. Zephyr has a lot more processor-specific assembly code, including much of the context switch code where the architecture-specific TLS hooks needed to go. It was easier to just do that part in line. After submitting the pull request, a couple of people who had been thinking about TLS support jumped in and made the rest of the TLS support part of Zephyr, and that series got merged in. But the main Picolibc integration hasn't been accepted yet. The initial blocker was a lack of toolchain support, which led to getting Picolibc integrated into Crosstool-NG, which led to fixing libstandard C++ to support other libc implementations. By then, I was off working on other things and unable to get back to Zephyr. I've got the patches rebased and working again. I'll try to see if I can get them posted and ask if somebody else wants to help bring this series home. Picolibc could also replace the built-in minimal C library in the Zephyr tree. The Picolibc code is smaller and faster in all cases, while also including a math library and other parts of a standard C environment. This could also replace the CB printf and printk paths in the system, reducing ROM prints quite a bit while improving standards conformance. There are always things to do with an old body of code like Picolibc. Some of the functions are still declared using KNR syntax. Much of the older and less frequently used code, like the search stuff, is still written with a casual approach to typing, leaving questions about integer overflow safety and the like. Similarly, the math library is showing its age, with numerous functions less accurate than many other C libraries like musl and glibc. This is especially true for odd corners of the library like tgamma and the Bessel functions. Picolibc can't simply adopt the glibc implementations given the licensing differences. I would also like to see integer-only implementations of some of the more important math functions for use on soft float hardware. To help people starting with a new device, it would be nice to include linker scripts and compiler options for a range of embedded SoC parts. That way you wouldn't have to dig through datasheets to discover where memory was mapped and what kind of core was provided. Finally, we're starting to see more activity with people using Picolibc, but it's still a pretty quiet project. And that's the end of my presentation. I hope you found it useful and want to thank you for taking time to listen today.